There's a certain magic in mathematics, a magic that connects the abstract to the real and the imaginary to the tangible. Among the countless equations that define our universe, there is one that stands out for its elegance and simplicity. This is Euler's identity. Imagine a journey that begins with a point, traveling along a path that curves and winds through the fabric of reality. Each step along this path reveals a deeper connection, a hidden truth that links the seen and the unseen, the known and the unknown. At the heart of this journey is Leonhard Euler, a soul whose boundless curiosity illuminated the world. His gift to us is the constant E, regarded as the second most influential number in all of mathematics by most mathematicians. The full beauty of Euler's identity emerges through the Taylor series, which deconstructs complex functions into infinite sums of simpler terms, namely polynomials. The more terms we have, the better the approximation. Here you see the Taylor expansion of e to the x, and here is the Taylor expansion of the cosine of x, and briefly we'll look at the Taylor expansion of the sine of x. It will be clear very soon why we're looking at all of these. Let's dive into the complex world. I will substitute ix in place of x, and we will end up getting the Taylor expansion of e to the ix. Notice something interesting, as the left side forms the Taylor series for the cosine of x, and the right side forms the Taylor expansion for I times sine of x. We can now write e to the ix as cos x plus I sine of x. Now, simply substituting for pi for x will give us the following expression, and we get e to the I pi is equal to -1. But what this expression is really saying is that we can think of e to the I alpha as a complex number with trigonometric coordinates, namely cosine alpha and I sine alpha. And that brings us inevitably to a whole new algebraic structure where all the possible values of e to the I pi lie in a circle, a complex circle. However, this expression also needs to align with this result. Do you remember the expression we introduced at the beginning? That's the e number limit expression. From there we can extend it for any power of x. And the question is, what happens when we plug I in place of x? In other words, what happens when x is equal to pi? Let's imagine that we have no idea. A very simple thing that we can do is to try substituting some values of n and calculate their different complex values. It might seem intimidating, but in the end, it is just a simple complex number that can be represented on a complex plane. If we continue this process as n tends to infinity, surprisingly we can observe that the values converge to -1. But this is not a proof at all, it is just an intuition. In order to prove this, we will split the path into partitions and show that the powers of the expression converge to -1 as the number of partitions goes to infinity. For example, for n is equal to 1, we have one possibility, and for n is equal to 2, we have two possible partitions. Notice that the height decreases and that these numbers are consecutive multiplications. And that leads us to a beautiful proof, where the path eventually converges to a half circle with radius equal to 1. And that leaves us with the final question. What happens when we plug into the expression x is equal to 2 pi instead? And what we find is even more surprising and just as beautiful, that the notion of the complex numbers lies in a circular structure. So again, we come back to the same idea, and that is truly remarkable, and probably the most beautiful proof in mathematics.